Okay. Good afternoon. Section 11.4. The comparison tests. So there are many sequences out there, many series, and very often it's difficult to study the divergence and convergence properties directly. But we have a very powerful tool of being able to compare something that we don't know to something that we do know. Okay? So there are two very important sequences. Important series are as follows. The geometric series. So we have A, R, n minus 1, okay, converges if R is less than 1, diverges if R is greater or equal than 1, right? We know everything about this series, okay? The second type of series is something that I asked the TA to cover in the last discussion yesterday. It's called the P series. The P series, okay? So it looks like this. 1 over n to the power of p, okay? It converges if p is greater than 1 and diverges if p is smaller or equal than 1. Okay? So let me give you very quickly some examples here in case you missed the discussion. So this one. Okay, this is a P series where P is equal to 1. So according to that rule, it diverges. And we also know that this is your harmonic series that diverges. So it diverges. Okay. The next example. This one. Here, P equals 2, which is greater than 1. We've seen this in class. It converges. Okay. And let me give you one more. This one. Okay. So what is the value of P here? 1/2. Less than 1. It diverges. Basically, when we have something like 1 over n to the p, the terms in this sequence have to decay sufficiently fast for it to converge. So if p is large, if it's bigger than 1, then this is pretty steep and it converges. If p is equal to 1 or less, then it's too flat and it diverges. Okay? So this is the second reference series that we're going to use. And it turns out that many other series behave like this, okay? Even though they don't look like them. So I'll give you a theorem, which is called the comparison test. So suppose that we have two series, AN and BN, okay? And let's suppose that they have positive terms. Okay, this is an important condition. And then there are two parts. Okay, if the B series converges and an is smaller or equal to bn, then an also converges. On the other hand, if bn diverges and an is greater than the other one, then an also diverges. Okay. This is almost completely exactly the same as the comparison test for improper integrals. Okay. We have one integral or series that we know something about. Okay. Bn is the one that we have studied, we know. For instance, it could be one of these. And we have something that we don't know anything about, a series an. So we can look at the behavior of the known series and then argue about the unknown one. If B converges and an is smaller, then an also converges. If B diverges and A is larger, then it also diverges. Okay, so it only works this way. So let's look at some examples, starting from more obvious to less obvious. Oh, and by the way, of course, the series B doesn't have to be one of these. As long as you know something about the behavior of B, you can apply this theorem. These are just two very good examples of a sequence where we know a lot about their behavior. So, the first example, let's consider the following series. Okay. So it's not something that we have seen before, right? But we can compare it with something that we have seen. So we can call it an, 5, 3n squared plus 2n plus 8. Okay. And for sure, this is less or equal than 5 over 3n squared, right? Because we add something positive to the denominator to make this smaller. Okay, so on the left we have our series that we want to study. On the right, we have a number times a p series with p equals 2. Okay, we know that this guy converges as a p series with p equals 2 greater than 1, right? So we know that. Therefore, 5/3 times this thing also converges. It's just a number times the convergence series. Okay. Therefore, our series, the unknown one, 5 over 3n squared plus 2n plus 8, also converges by comparison test. Each of its terms is smaller than the terms of a convergent series. And also they are positive, right? I didn't check that explicitly, but you can see that all the terms are positive because n goes 1, 2, 3, 4, 5. So there's no negative numbers here. Okay, so this is a very easy example because you add stuff to the denominator, so you make it smaller. You can easily compare this expression to this expression. Questions? So the next one is a little bit less obvious. Let's look at this one. So 1 over n squared, n squared minus 2.9. 9.2. 9.2. Okay, so I would like to compare it to something that looks like it and something that we know the convergence of. So I want to compare it to 1 over n squared, right? So let's see. So this is my given term of the sequence. And I have this. Unfortunately, I'm not adding to the denominator. I'm subtracting from it, right? So this is actually greater than this. I know that this converges, but the convergence of this series doesn't tell me anything about this one. It's bigger than this, so in principle it could diverge. Okay, and this is not the result that I want. So I want to find a sequence that this is smaller than my sequence. So I'm going to try something slightly different. So I'm going to say that perhaps I can compare it with 2 over n squared. Okay, I multiply the p series by 2. Okay, and I want to see, is it true? Right. It's not immediately clear, but let's just try. So you know that it kind of behaves like 1 over n squared. The intuitive reason is the following. You know there's an infinite number of terms here. And when n becomes large, this number becomes really huge. For instance, when n is equal to 100, this is 10,000. And this is 9. What is 9 compared to 10,000, right? When this is a million, and it goes much more than a million. When this is a million, this is, I don't even know what it is, 12 zeros. This is 9. Okay, so in principle, all the terms look very much like this. Okay, so somehow it should behave like it. But unfortunately, we cannot use the comparison in this way. So we're going to use a trick. We multiply this sequence by 2 and see for what values of n this holds, because this is the inequality that I want. So let's multiply through by n. So I have n squared is less or equal to 2n squared minus 18 times 4. Okay, I brought it to the common denominator and ignored the denominator, assuming that it's positive. So that gives me n squared is greater than 18.4, or n greater than square root of 18.4, which is approximately 4.3. So if n is greater than or equal to 5, then my given sequence is actually smaller than 2 over 9 squared. So now I can reason about this one. Okay, I can use this P series to draw conclusions about my given series. Because 1 over n squared converges, so does this. Okay. Questions? Question?
Yeah, can you explain that little step over there?
So let's see when this inequality holds. Okay. So presumably, when n is large, it's going to hold. So I'm going to multiply across by the 2. So let's assume that n is greater than square root of 9.2. Okay, I have to assume it here. So the denominator is positive. This is positive. I can multiply across. So I have.
I thought that was
So this is a result of bringing it to a common denominator. Then I can cancel the denominator, and the rest follows. Okay. More questions? So one remark here is that, okay, this inequality actually doesn't hold when n is smaller, right? But I don't care as long as it holds for n starting from some finite value all the way to infinity, because it's the infinity that I care about. A finite number of terms for which this inequality doesn't hold doesn't bother me, because they add up to a finite number. What influences the convergence is the behavior at infinity. So as long as I can prove this inequality for all values of n starting from some number, then I'm fine. Question?
How do you know when to pick 5 or if like n is greater than or equal to?
So I got this number, 4.3.
Yeah.
Because n is an integer number, I'm guaranteed that starting from 5, it's going to hold.
So you know that the set limit's going to be convergent because it's less than 5 or greater than 5?
Sorry?
So why can you explain this the step in this side?
So I know that if n is greater than approximately 4.3, the terms an of my given series are less than bn of this series.
Oh.
This inequality holds for n equal to 5, 6, 7, 8, and all the way up to infinity. Okay? So as long as this holds, I apply my comparison test, and then it works. Okay? More questions? Okay. One more. Something that diverges. Okay, let's do something that diverges. So let's look at log n over n. I think we've seen this before, and we used a different method. We used the integral test, yes. But now we're going to use a comparison test. So bn are my terms, log n over n. And I want to compare it 1 over n. This is a harmonic series that diverges. So if I can show that this is greater than this, then my given series will diverge. So is it greater than 1 over n? Not always. Okay, it's not always greater. For instance, when n is equal to 1, this is actually 0, right? So we have 0, and here we have 1. So this doesn't hold. But for other values, we may have it may hold. So we observe that. So we have to have log of n greater than 1, right? Log n is greater than 1 for n greater than e. Okay? Starting from, for instance, n equals 4, 5, and so on, we have an, which is log n over n, is greater than 1 over n, which is bn. We know everything about this sequence. This is a harmonic sequence, harmonic series, diverges. So this diverges, and this is even bigger. It's greater than the diverging sequence, so it diverges itself. We conclude that log n over n diverges by comparison test. Okay. Questions? Okay. Let's see. Sometimes it is difficult to show these inequalities. Like this one was a little bit messy. You saw that we had to use some tricks. We actually had to multiply this guy by a number to show that the given sequence is smaller than what we want, right? So it's not always easy. There's another way, and it's called the limit comparison test. So this is a very nice theorem that allows me not to worry about inequalities, basically, and missing a sign or something. So suppose that we have, again, two sequences. Whenever we have a comparison test, we're going to have two objects. One is unknown, and the other one we know something about. And we're going to compare the new one to the old one and draw conclusions, right? So suppose we have two sequences, AN and BN, and they have positive terms. Okay. Then we have to look at the limit. Instead of looking at inequalities, we're going to study limits of the following object. Okay. Where C is finite and C is greater than 0. Okay. Then either both series converge or both diverge. So if this limit kind of tells me that they behave in the same way. They differ by a constant as n becomes very large. So let me show you an example. So let's look at the following sequence. 1/2 to the n minus 55. Okay. So first of all, this thing has to have positive terms. And obviously, this one doesn't have all the positive terms. For instance, when n is equal to 1, this is 1/minus 53. But as n becomes large, starting from some value, all the terms become positive, and that's all I need. Again, I only have to worry about the infinite tail, starting from some finite value. Okay, so starting from some finite n, all the terms are positive, and so in our notations, this is the unknown sequence. What is the sequence that I want to compare it with? I see that we have a constant here, but we have 1/2 to the n. And that's a good one, because this is a geometric series. So we want to compare it with the sequence Bn, 2 to the n. Right? Which we know this one converges, because it is a geometric series with r equals 1/2, less than 1. Okay. So that's a good one. Now we want to implement this test. So instead of comparing directly an to bn for each n, we are going to look at the limit as n goes to infinity of an over bn. So let's write it. An is that thing, 2 to the n minus 55. And this one is 2 to the n. Right? So I formed the ratio of the two. And the goal is to show that it tends to a positive constant. So what are we going to do? How do we evaluate something like this? We're going to divide numerator and denominator by 2 to the n, right? So we have 1 minus 55 over 2 to the n, right? This is the way to evaluate this limit. And as n goes to infinity, 2 to the n becomes very large. 55 divided by this number vanishes, okay? So the limit is 1. And of course, 1 is greater than 0, right? It's a positive non-infinite number. So Bn converges by the limit comparison test. By the limit comparison test. Questions? Question?
You mean AN, right?
Oh, yes, AN, thank you. Absolutely. Do you have the same question? Yes. So let me give you a more sophisticated example. So we're going to look at the following series. 3n cubed plus 2n squared cube root of 1 plus n to the 10. Okay? Something completely crazy. So we have to kind of figure out what to compare it with. And so over here, in the previous example, we kind of look at the leading term in the numerator and denominator. Okay? Here the leading term is 2 to the n, and that's the one we keep, and that's the one we use. Okay? Here we're going to do the same. We look at the biggest contribution in the numerator and in the denominator as n goes to infinity. So what's the largest term in the numerator? This definitely wins, right? This is a cube power of n, and this is second power. So this is a bigger contribution. In the numerator, this is a lot bigger. Okay? So I'm going to create a sequence that only has the leading order terms both in numerator and denominator. So let's set Bn to be 3n cubed divided by cube root of n to the 10. Okay? And this is the trick that you can always use to kind of figure out what to compare it with. Okay? The resulting sequence will have to be a p sequence because it's going to be some power of n. So what power of n? We'll have 3 times n cubed. And here we have n to the power 10^3. So what do we get? We get 3. And this is 3 1/3. So this is n 1/3. Right? So this is a p sequence. A p sequence with p equals 1/3. What does it do? Does it converge or does it diverge? This diverges because this is less than 1. Diverges. So if this one diverges, then perhaps the given one also diverges. But what we have to show is the limit comparison test. We have to look at the limit of the ratio of the terms. So use the limit comparison test. So here you can kind of see why I don't use the straightforward comparison test. The first comparison test, we would have to prove that these terms are smaller than these. And this is a very difficult task because the functions that are involved are horrible. Okay, it would be a lot of work to show that something like this is always smaller than something like this. Now, when you take the limits, it becomes easier, as you will see. So in the previous example, we could use either test. Here, I would advise against the straightforward comparison test. And I would suggest to only use the limit comparison test. So we have to consider the limit as n goes to infinity of an over bn. So what is this? I have to rewrite this whole thing. 3n cubed plus 2n squared. Like this. And now I have 3, and here I have n 1/3. Right? So how do I modify it to get something decent out of it? First, I'm going to multiply through the numerator to simplify it. Okay? So I have 3. So the total power of n in the first term is 3 plus 1/3. So this is 10/3. Okay? Plus 2. And I have 2 plus 1/3. That's 5/3. And the denominator remains the same. Okay. So now I'm in a better position to do something because I can use the usual trick. I divide everything by the greatest power of the numerator. Question?
How about the 3
I forgot it. Thank you. So we look at the numerator. This is the biggest power, and we divide by it. Question?
Would it be 2 to the 7/3 power?
That's entirely possible. What's 2 times 3? It's 6, right? So it's 7. Thank you. 2 n. Thank you. Okay. So divide here by n 10/3. Okay. Limit as n goes to infinity. What do I have? 3 plus 2. So minus n to the minus 1, right? I think. And here I have 1 n minus 10 plus 1 over 3. Okay? Because when I divide the denominator, it's under the cube root. So when n to the 10/3 makes its way under the cube root, the power becomes n to the 10. So I divide under the root, I divide by n to the 10. So I have n to the minus 10 from this, and this gives me 1. Okay. The third radical. Thank you. Okay. Now it's easy. Now everything is easy. So this goes to 0 because it's 1 over n. This obviously goes to 0 too. What do I have left? I have 3 divided by cube root of 1 times 3. So it's 1. So this satisfies the requirement of the limit comparison test. It's a constant greater than 0. Therefore, an diverges 2. Just like this sequence. Okay. It behaves, in terms of convergence, it behaves the same as the sequence that we're comparing it with. Questions? Okay. Let me show you how to prove this last theorem. It's a very easy and straightforward proof. So we're going to prove the limit comparison test. So suppose, so we have the limit as n goes to infinity of an over bn is given by c, right? C is a non-zero is a positive number. So suppose that there are numbers m and m such that m is less than c and that's less than m. We can always find a pair of numbers like this. Okay, not necessarily integer numbers, any numbers. Now we can say that because the limit of an over bn is equal to c, starting from some n, this sequence is going to be very, very close to c, right? That's the meaning of limit. So if the limit of this guy is a number c starting from some n, it's going to be very close to it. How close? Well, arbitrarily close. For instance, it could be closer than either m or m. It could be so close to c that it's also within these bounds. So we can write that it makes it inside this interval imposed by my two numbers. Okay? Because the terms of my sequence are are positive, we can multiply this whole thing by bn, and we have bn less than an bn over m. Okay? And this is pretty much all we need. Because now this theorem looks very much like a comparison test. So look, if bn converges, then of course m bn also converges. And then you can see that an is smaller than this. We'll look at the right-hand side. Okay? An also converges by a comparison test. Okay? On the other hand, if bn diverges, then so does m bn. It also diverges. And now I'm going to use the left-hand side of this inequality. An is bigger than this. It's bigger than something that diverges. So an also diverges by comparison test. So this limiting version of the comparison test can be reduced to the straightforward comparison test. Okay? It amounts to the same thing. Questions? Okay, very good. So according to our syllabus, we have to cover 3 sections in 2 lectures. So I'm going to start on section 11.5. I know. We do something easy, okay? Beginning is always easy. Alternating series. What's an alternating series? Here's an example. Okay. This is a series whose terms alternate in sign. And an example, this example comes from taking the harmonic series and alternating the signs. Okay, it's a modification of that, but it turns out that it has very different properties. Okay, so how can we write this down in terms of one formula? We already saw that. So each term, its absolute value, is given by 1 over n, but the signs alternate. Right? The first sign is positive. So we have minus 1 to the power of n plus 1. So this guy here is a little machine that creates alternating signs, right? When n is odd, the sign is positive. When n is even, the sign is negative. That's how we want it. If my sequence starts with a negative term, we will have minus 1 to the power of n. Actually, this is, let's look at this. So we have minus 1 plus 1 over 4 minus 1 over 9 plus 1 over 16. What is that? So each term looks like 1 over n squared, okay? And it has alternating signs. So I have minus 1 to what power? The first one is negative, so the even ones have a negative sign. So it's minus 1 to the n. So let me summarize it here. Minus 1 to n plus 1 gives positive odd terms. And minus 1 to the n gives negative odd terms. So depending on where you start with, you use the right one. Okay. So it turns out that it's easier for alternating series to converge. So if the sign doesn't alternate, we have a harmonic series, and we know that it diverges. But when they alternate, I don't always add. I sometimes, in fact, half of the time I subtract. So this has a chance of actually being convergent. So let me state a theorem that makes this rigorous. So it's called alternating series test. So if we have a series like this, minus 1 to the n plus 1 bn satisfies sorry, let me just write with positive bn's, okay, satisfies two conditions. Okay, I'm going to give you two conditions. Then the series converges. So what are the two conditions? The conditions are going to be on the terms bn. So the first condition is bn plus 1 has to be not bigger than bn for all n. And the limit, as n goes to infinity, of bn has to be 0. Okay, so this to see this, let's ignore for now the sign, okay, and only look at the absolute value of each term. So there are two conditions that these absolute values have to satisfy. First, they have to go down in size. The absolute value has to be smaller and smaller and smaller. That's the first condition. And that's not enough. They have to go down to 0. Okay? So it's possible that only one of these conditions is satisfied and not the other. For instance, they could go to 0, but they can go up and down like this, right? Bigger, smaller. So that would not be enough. We have to have both conditions. So let's check. Let's use the example of the alternating harmonic series. Okay? Check 1 and 2. So what is Bn? Bn is 1 over n in this case, right? So the first condition states that Bn has to be smaller or equal. Bn plus 1 has to be smaller than Bn. So let's write that down. Bn plus 1 is just 1 over n plus 1. And this is 1 over n. Does the inequality hold? Yeah, it's quite clear that it does, because we add 1 to the numerator. Okay, so this is good. The second condition is the limit as n goes to infinity of Bn. This is usually really easy to check. Okay, what happens here? Limit as n goes to infinity of 1 over n. What is this? 0, quite clearly. So both conditions hold. So we conclude that this alternating series converges. Okay? Its harmonic brother, the one whose terms don't alternate, diverges. But as soon as we stick in minus 1 to n plus 1, it diverges. It starts converging. Okay? So to see this, I'll show you intuitively what this means. Why does it work like this? So I'm going to plot a number line, okay? And let's suppose that this is 0. And we're going to look at partial sums, which are here's I. We have to add from 1 to n. Okay? So what is S1 is just minus 1 S1 is just B1. S2 is B1 minus B2. S3 is B1 minus B2 plus B3. S4 is B1 minus B2 plus B3 minus B4. Okay? So we're going to look at these things. So S1 is B1. Let's go S1. Okay. Now let's look at S2. S2 is smaller than S1 because we subtract a positive number. And we can also see that it's greater than 0 because the terms decay. B2 has to be smaller than B1. So S2 has to be somewhere here. Now we look at S3. S3 is equal to this guy, S2, and we add a positive number, right? So it's going to be bigger than this. But by how much? Is it going to go on the right of this or on the left? Because these terms get smaller and smaller, the ones that we add. It's not going to go all the way here. It's going to end up somewhere here. So that's S3. S4 is going to be smaller again, okay, but not quite all the way here. So they're going to oscillate with a decreasing amplitude. So it's going to go right and left, but it's going to jump less and less, until it settles somewhere. So this is the intuitive reasoning behind the alternating sign test. Okay? When we don't have minus 1 to this power, what we have is S1, then we have S2, S3, S4, that diverges. Okay? Here, they jump around, and they remain bounded, for sure, between S1 and S2, and it takes a few more lines to show that they actually converge to a finite limit. Questions? Thank you very much.